Okay.
Okay, welcome everybody to attend the evening session of the first day's lecture. And the first speaker this evening will be Osamu Fujino from Kyoto University. And the title is, I think, on your screen.
Yeah. Okay. Thank you very much. First of all, I thank the organizers for giving me this opportunity. And good evening. In Japan, it's morning, but and long time no see. Yeah. And happy birthday, Professor Shokurov.
Thank you. Thank you.
Yeah. Yeah. And the title is Vanishing theorems for projective morphisms between complex analytic spaces. And today I'd like to, I'd like to talk about vanishing theorems in complex analytic spaces. Okay. In my talk, I am only interested in complex analytic spaces. Okay. Okay, let's go to the first slide. Okay, in this slide, I would like to talk about my motivations and background of this talk. Okay, I am mainly interested in the minimal model program for projective morphisms of complex analytic spaces. Okay, in order to study complex analytic singularities, for example, let X be a complex analytic singularities, then we can always take resolution. So we get a projective bimeromorphic morphism from a complex manifold. If we can formulate and establish the minimal model program for projective morphisms between complex analytic spaces, then we can run a minimal model program for such resolution. And we finally obtain a good partial resolution of given complex analytic singularity. And so we can use minimal model program for the study of complex analytic singularities. And we sometimes have smooth projective family of complex analytic complex projective varieties over punctured disk and want to study special fibers. So in that case, we take semi-stable reduction and we get a semi-stable family of algebraic varieties. And if we can use a minimal model program for projective morphisms of complex analytic spaces, we can run a minimal semi-stable minimal model program in order to study special fiber. Okay, disk is not an algebraic variety; it is only a complex analytic space. So I think I am interested in minimal model program for projective morphisms of analytic spaces. Okay, and I think it is well known that the Karmata-Fibek vanishing theorem can be proved for complex analytic spaces of projective morphisms of complex analytic spaces. This is because KLT pairs can be characterized by using L2 condition, and so we can use L2 method for the study of Karmata log terminal pairs. Okay, so we can use
We lost the sound.
Osamu, are you muted?
I think you're muted.
Okay.
Yeah, that's
Yes.
okay.
Okay. Okay. Anyway, Karmata-Fibek vanishing theorem is known to hold for projective morphisms of complex analytic space. Because we can use L2 method, so we can use Osa's vanishing theorem and Takegoshi's vanishing theorem and so on. So there are no problems for Kamata feedback vanishing theorems. And it's sufficient for the study of Kamata log terminal pairs, I think. So I think almost everything established by BCHM holds for projective morphisms of complex analytic spaces, I think. But I am mainly interested in complex analytic spaces whose singularities worse than Kamata log terminal singularities. I am mainly interested in log canonical pairs and much more general objects, Kaji-log structures, which was first introduced by Florian Ambro on complex analytic spaces and so on. So we need much more powerful vanishing theorems than Kamata feedback vanishing theorems. Okay, this is my motivation and background. Okay. Okay. Let's recall Kollár's theorem. Okay, it was obtained in 1980s. Now it is a well-known classical result. Okay, the situation is as follows: Fx to YBR surjective morphism of complex projective varieties, and X is smooth and Y has any complex projective varieties. The first statement is known as torsion freeness. Okay, higher direct image of canonical bundle is torsion free C for every Q. Okay, this is the first statement, and it is a generalization of Gravel-Riemann-Schneider vanishing theorem. For example, F is generically finite and Q is positive, then this CF is automatically torsion C, and torsion freeness implies this CF is 0. Okay, so it's a generalization of Gravel-Riemann-Schneider vanishing theorem. And the second one is known as Kollár's vanishing theorem. Okay, let A be an ample line bundle on Y. Y is any projective variety, so we can always find an ample line bundle. Then the cohomology, higher cohomology of this CF, A times higher direct image of canonical bundle is 0. This is known as Kollár's vanishing theorem. And this vanishing theorem is a generalization of Kollár's vanishing theorem. So we put X equal Y, and the morphism is F is identity, and the Q equals 0. Then Kollár's vanishing theorem recovers Kodaira vanishing theorem for projective varieties. Originally, Kodaira formulated his vanishing theorem for compact complex manifold and positive line bundle. But once we know the Kodaira embedding theorem and Selz-Gaga theorem, Kodaira's vanishing theorem is a theorem for projective varieties with ample line bundle. Okay, so it is a special case of Kollár's vanishing theorem. Okay, and this is first statement is torsion freeness, and second one is vanishing theorem. And Professor Kollár simultaneously proved injectivity theorem. And we know injectivity theorem is equivalent to theorem 1. Okay, so in algebraic situations, we usually first prove injectivity theorem, Kollár's injectivity theorem, by using Hodge theory. And then, as an application, where we can prove torsion freeness and vanishing theorem. But once we know torsion freeness and vanishing theorem, we can recover Kollár's injectivity theorem. So theorem 1 and Kollár's injectivity theorem is equivalent. Okay, and theorem 1 is formulated for projective varieties, but it's okay for even when X is a compact Kähler manifold and Y is a projective variety. Okay, and we can prove this theorem by using E1 degeneration of Hodge-2 drum type spectral sequence. of smooth projective varieties. More precisely, we take some cyclic cover of X and take a resolution and consider Hodge-to-Drum type spectral sequence on that smooth projective variety. And by using the E1 degeneration, we can obtain injectivity theorem, Kollar's injectivity theorem. And as an application, we can recover theorem 1. This is a standard technique for algebraic varieties. And in this case, X is a smooth projective variety, and so everything is compact. So we can use a global result, global Hodge theory. So there are no difficulties now. Yeah, but sorry. Okay. Oh, okay. But in this talk, I am mainly interested in complex analytic spaces. Okay. Okay, let's go to Takegoshi's theorem. It is a direct generalization of Kollar's result, theorem 1. The statement is very similar. Fx to y be a proper surjective morphism from a connected Kollár manifold X to a complex analytic space Y. The first statement is the same as Kollar's. Higher direct image of canonical band is torsion free for every Q. Okay, completely the same, but the difference is in the setting. X and Y be a only proper surjective morphism of analytic spaces. Okay, and the second one is vanishing theorem. Y to Z be a projective morphism of complex analytic spaces, and curly A be a pi ample line bound on Y. Then this C, higher direct image of A tensor RQ F pushward omega X equals 0 for every positive P and every Q. Okay. So this is a complex analytic generalization of Kollar's torsion freeness and vanishing theorem. Okay. And the key point is here. In theorem 2, X and Y are not necessarily compact. So we cannot directly use global result, global Hodge decomposition, and so on. So the proof is much more difficult than Kollar's theorem. And theorem 2 is a special case of Takegoshi's result. Takegoshi obtained much more general results. For example, Takegoshi's theorem holds for canonical bundle, tensor, Nakano semi-positive vector bundle, and so on. And Takegoshi's result is much more general than theorem 2. Okay, and theorem 2. In order to prove theorem 2, Takegoshi discussed the theory of harmonic homes. Okay, he discussed the harmonic homes with Neumann condition on a smooth scalar manifold with boundary. Okay, so he represents some cohomology by the space of harmonic homes and obtained these results. Okay, so anyway. The statement is very similar to Kollar's original statement, but the proof is much more difficult. The difficulty is here. In theorem 2, X and Y are not necessarily compact. So if X and Y are both algebraic, then we can always compactify. But in this setting, X and Y are only complex analytic space, so we cannot always compactify. So we have to treat complex analytic objects. Okay. Okay. So in this talk, I would like to generalize Takegoshi's theorem for much more general setting. For example, X is a simple normal crossing variety, and so on. Okay, so we need the definition of simple normal crossing pairs and globally embedded simple normal crossing pairs. Okay. Okay. Let's introduce globally embedded simple normal crossing pairs. Okay. in definition 3, M is a smooth complex analytic space. So M is a complex manifold, and X is a simple normal crossing divisor on X, on M. Okay, and X is reduced. Okay, X is a reduced simple normal crossing divisor on a smooth complex analytic space M, and B being an R divisor on M, such that support of B plus X is a simple normal crossing divisor on M, and B and X have no common components. In that case, we can define restriction of B to X. We put it to D and call the pair X delta XT analytic globally embedded simple normal crossing pair. This type of object often appears in various geometric applications. Okay. For example, M is a resolution of some singular variety, and B plus X is inverse union of the inverse image of given device.
You're hungry, Michael?
Yes, very.
Sorry. Okay. P plus X is the union of strict transform given divisor and exception divisor. And X is a reduced part of that divisor, and B is another divisor. This is a standard object, I think. And the simple normal crossing pair is an object locally isomorphic to a globally embedded simple normal crossing pair. So the pair XD is locally isomorphic to a globally embedded simple normal crossing pair at any point. And we first assume every reducible component of X and D are all smooth. Then XD is called the analytic simple normal crossing pair. Okay. As I explained, this type of object often appears in the minimal model program. M is a resolution of some singular variety, and B plus X is the union of exceptional divisor plus strict transform of some divisor, and X is a reduced part of that divisor. Okay. So this is a very important object, I think.
So do we need B and D to be effective or not?
B is any divisor, not
Okay.
necessarily effective. Okay. X is reduced and B is another part. And yeah, and sometimes B has a reduced part. Okay. Okay. Next one is very complicated. The composition of XD. XD being analytic simple normal crossing pair. So X is a simple normal crossing variety, and D is a divisor whose support is as good as possible. And we further assume D is reduced. This means the quotients of D is all 1. Okay. In that case, we put xk, x upper k is like this. Okay. And tilde means the normalization of z. Okay. So x1, k equal 1 case is a disjoint union of irreducible component of x. Okay. So small k equal 1, then xk is a normal, nothing but x1 is nothing but the normalization of x. So x1 is the disjoint of each irreducible component. Okay, and x2 is the disjoint union of the intersection of 2 irreducible components of x, and x3 is intersections of 3 irreducible components of x, and so on. So this is yeah. Please imagine the picture. Sorry, I cannot draw the picture. Yeah. Okay, and dk is defined by the pullback of D by the natural morphism xk to x. Okay, so x1 is a normalization of x, and so D1 is the pullback of D to the normalization, and we define dkl like this. Okay, so multiplicity is dk is less than or greater than less than or equal to L, then we put dkl. Okay, so dkl is a disjoint of smooth variety, smooth complex analytic space, and dk0 equal the xk by definition. Okay, L equals 0, then we can recover xk, dk0 equal xk, and by definition, dkl equal dimension of dkl equal dimension x plus 1 minus k minus l. Okay, so the dkl is a smooth complex analytic space, and there are many irreducible components, but it is equidimensional. Okay. Okay, it's very complicated, but yeah, please draw pictures by yourself. Okay. Then we can construct the following spectral sequence. This is the main ingredient of this talk. Okay. Let X be an analytic simple normal crossing pair such that D is reduced. This means every question of D is 1. And if X2Y be a proper morphism to a complex manifold Y, okay, Y is a complex manifold. And we further assume that F is scalar on each irreducible component of X. So the definition of Kollár morphism is not so easy. So if you are not interested in Kollár morphism, so simply assume each irreducible component of X is Kollár. Okay, it is similar to the condition that each irreducible of X is Kollár manifold. Anyway, in some Kollár assumption, then there is a weight spectral sequence degenerating at E2. Okay. E1 term is like this. This is a well-known object. DKL is a disjoint of smooth complex analytic space, and E1 term is push forward of higher direct image of canonical bundles. And yeah, and this spectral sequence degenerates at E2, and the key point is here. Each E1 differential D1 splits so that the E2 term are direct factors of E1. This is very, very important. And this theorem follows from Saito's theory of mixed Hodge modules. So first we consider mixed Hodge module of X minus D and push forward and consider compact support cohomology, and we get this type of spectral sequence. First, we construct a spectral sequence for mixed Hodge modules, and take the bottom Hodge filtrations. We obtain this type of spectral sequence. And E2 degeneration follows from Saito's theory of mixed Hodge modules. And key point is splitting of D1. This follows from the semi-simplicity of polarizable pure Hodge modules. Okay, so it is very strong property. Polarizable pure Hodge module is a semi-simple object, and we can always take splitting. Okay, and the proof of theorem 6 it becomes when F is projective. Okay, when F is projective, we can use the standard framework of Saito's theory of mixed Hodge modules. But when F is only Kollár, I think we need a much more difficult result, decomposition theorem of Kollár morphism. And sorry, I don't understand the Kollár case, but yeah, but yeah, anyway, by using Saito's theory of mixed modules and F is projective, so we can use the standard framework of Saito's theory of mixed module. We get this spectral sequence. Okay, and okay, and yeah, and yeah, okay, sorry. Okay. And in order to state our main result, we recall the strata of XD. Okay. Strata is a generalization of DKL. DKL defined in the previous slide. Okay. Let XD be an analytic simple normal crossing pair. So X is in general simple normal crossing variety, and these are divisor whose support is as good as possible. And let nu, x nu to x be the normalization, and we can define theta. Theta is the inverse image of D, and union of the inverse image of D and singular locus of X. Okay, a singular locus of X corresponds to the conductor divisor. Okay, so anyway, we can define theta on X nu. And if W is an irreducible component of X, or the new image of some log canonical center of this pair, X nu theta, then W is called the stratum of XD. Okay. In general, in this definition, D has any device, any coefficients. D is not necessarily effective. Okay. And we can define stratum of XD by this definition. Okay. And when D is reduced, so the questions of D is all one. Then W is a stratum of XD if and only if W is the image of an irreducible component of DKL defined before for some K and L. Okay. So if D is reduced, stratum means irreducible component of some components of X and D. Okay, so if D equals 0 and X equals 0, X is only simple normal crossing variety, then stratum is nothing but the usual one. Irreducible component of X and irreducible component of some intersection of irreducible component of X. Okay, so strata of a generalization of DKL defined before. Okay. 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 This is a generalization of Kollar's theorem and Takekoshi's theorem. Okay. XTB and analytic simple normal crossing pair such that D is reduced. So the questions of D is 1. And fx to y be a proper morphism of complex analytic spaces. And we further assume f is scalar on each reducible component of x. And I am mainly interested in the minimal model program. So for applications, f is always projective. So there are no problems on this assumption. And if each irreducible component of x is scalar, then f is scalar on each irreducible component of x. So sorry, I do not define scalar morphism precisely, but yeah. So this condition is not so serious for application. Then the first one is a generalization of Kollar's torsion freeness and Takekoshi's torsion freeness. We call it strict support condition following the theory of mixed Hodge modules. Every associated subvariety of this coherent C is the F image of some stratum of XT for every Q. Okay, if X is smooth variety and D equals 0 and F is surjective, then this statement says every associated prime of this C is the generic point of Y. This is nothing but torsion freeness. But in our case, X is reducible and D has many components, and so there are many associated subvariety. But we can control the associated subvariety of this coherent CF by the geometric data of XD. Okay. And the second one is similar to Takegoshi's vanishing theorem. Y2Z be a projective morphism of complex analytic spaces and A be a pi ample line bundle on Y. Then higher direct image of this C equals 0. Okay. Statement is very similar to Takegoshi's theorem, but in our case, D is not necessarily 0 and X may be reducible. So much more general than Takegoshi's theorem. Okay. And the proof is not so difficult, I think. Sorry. Theorem strict support condition is almost obvious by theorem 6. Okay. Theorem 6, please remember this one. So in this statement, even term is direct sum of higher direct image of smooth variety. Okay, and we can apply Takegoshi's theorem, so we can check even term satisfies strict support condition. Okay, and by this statement, each term are direct factors of E1. So each term satisfies strict support condition. Okay. And there exists a finite weight filtration, and so by using short exact sequence, we get to the strict support condition of the right-hand side. Okay, yeah, this is a proof of theorem strict support condition. Please note that in theorem 6, Y is a smooth complex manifold, but in theorem 8, Y is only complex analytic space, but locally we can always embed Y into a polydisk. So we may assume Y is a polydisk. So we can apply theorem 6 directly, and we get strict support condition. So strict support condition is direct follows from theorem 6. Okay. So strict support condition is a consequence of the strict support condition of polarizable pure Hodge modules. Okay, polarized pure Hodge modules has strict support condition. Okay, and second one is we can check this vanishing theorems by using the spectral sequence obtained in theorem 6 and Takegoshi's theorem. Yeah. So as in the strict support condition, we can assume Z is a polydisk and Y is embedded into polydisk times some projective space, and so we can assume Y is smooth variety, and we can use theorem 6. Okay, and by Takegoshi's theorem, we can obtain desired vanishing theorem for E1 term, and each term are direct factors of E1 term. So we get some vanishing theorem for each term, and there exists a finite weight filtration, and by using the short exact sequence, we get a vanishing theorem for the right-hand side. This type, yeah. So by using the spectral sequence and Takegoshi's vanishing theorem, we can recover this theorem. Okay. So anyway, we can prove vanishing theorem and strict support condition, which is a generalization of torsion freeness. Okay. Okay. So anyway, theorem 6 is a main ingredient of this proof. Okay. And by using theorem 8, we can recover Kollár's injectivity theorem in much more general setting. Let XD be XD and X to Y be as in theorem 8. So XD is simple normal crossing pair, and D is reduced, and fx to y be a morphism, which is scalar, scalar on each reducible component of x, and L be a F semi-ample line bundle on X, and small s be a non-zero element of this global section. And we assume the zero locus of S does not contain any strata of XT. This is a very important assumption. Then this map induced by the tensor product of S is injective for every positive L. Okay. This is a generalization of Kollár's injectivity theorem. Okay, if y is a point and x is irreducible and equal d equals 0, then we can recover Kollár's injectivity theorem. Okay, so y is a point and x is a smooth projective variety and d equals 0. So this is a cohomology of omega x tensor L, and yeah, it is nothing but Kollár's injectivity theorem. Okay, and this is a routine work to prove theorem 9 by using theorem 8. Okay, as I explained, injectivity theorem is equivalent to torsion-free plus vanishing theorem. So usually for algebraic varieties, we first prove injectivity theorem and then get to vanishing and torsion freeness. But in our case, in this case, we first prove vanishing theorem and strict support conditions. But I think it's a routine work to recover injectivity theorem by theorem 8. Okay. Anyway, we can prove injectivity, vanishing, and torsion freeness in much more general complex analytic setting. Okay, and I think theorem 8 is very useful, but I don't know theorem. I don't know if theorem 9 is useful or not. Okay. 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 This is the main theorem. Okay. Let X delta be an analytic simple normal crossing pair, and delta is a boundary R divisor on X. A boundary means the quotient of delta is delta is effective, and the quotient of delta is less than or equal to 1. This is a definition of boundary R divisor, and fx to y be a projective morphism to a complex analytic space. Okay, so in this theorem, we assume F is projective. And L be a line bundle on X. Okay, and small q is an arbitrary non-negative integer. Okay, the first one is a generalization of torsion freeness. L minus omega x plus delta is F semi-ample. Okay, then every associated subvariety of this C is the F image of some stratum of X delta. Okay, so if the delta equal reduced and L equal omega x plus delta, then this is nothing but theorem 8. But in our case, delta is a boundary R divisor, and L minus omega x plus delta is F semi-ample, so it's much more general than theorem 8. But we assume F is projective. Okay. And the second one is vanishing theorem. L minus omega x plus delta is pullback R linearly equivalent to pullback of H. And H is a pi ample R line bundle. So this means positive R linear combination of ample line bundle. And Y to Z is a projective morphism to a complex analytic space. Then this type of vanishing theorem push forward a higher direct image of RQF push forward L equals 0 for positive P. Okay. Of course, this is a generalization of this vanishing theorem. Okay. Okay. But in theorem 10, we assume F is projective. Because we take some cyclic cover and so on, so we need ample divisor. So fx to y we assume fx to y be a projective morphism. Okay. And when fx to y and pi y to z are all algebraic, then this theorem is already well known. Okay, I think first obtained by Eno, Fiebeck, Ambro, and yeah, and so on. Okay, yeah, and I used this type of vanishing theorem and strict support condition for the study of log canonical singularities and Kaji-log structures on algebraic varieties. Okay, but in theorem 10, fx to y and pi y to z are only complex analytic projective morphisms of complex analytic spaces. So theorem 10 is much more difficult than algebraic varieties for algebraic varieties. And yeah, this theorem will play a crucial role for the study of complex analytic log canonical singularities and Kaji-log structures on complex analytic spaces and so on. And yeah, I think by using this vanishing theorem and this strict support conditions, we can establish, for example, Kohn and contraction theorem for log canonical pairs and so on. And please note that the Kohn and contraction theorem for KLT pairs is known even for complex analytic spaces. Yeah, it is essentially due to Nakayama, which was obtained in 1980s, but for log canonical pairs, it is not known. But I think by using this type of theorem, we can prove Kohn and contraction theorem and so on for log canonical pairs for projective morphisms of complex analytic spaces. Yeah. Now I'm checking the details. Yeah. And the final theorem, this is the final one. For many applications, the vanishing theorem discussed in theorem 10 is sufficient, I think. But this is a slight generalization of vanishing theorem in theorem 10. It is usually called Reed-Fukuda type. Let X delta be an analytic simple normal crossing pair such that delta is a boundary R divisor on X. And fx to y and y to z be projective morphisms of complex analytic spaces, and L be a line bundle on X. This condition is same as theorem 10, but here L minus omega X plus delta are linearly equivalent to pullback H. And in theorem 10, H is a ample line bundle, ample R line bundle. But here we only assume H is an R line bundle, which is nef and log weak over Z with respect to this morphism. This means the restriction of H to the image of some stratum of X delta is nef and B. So if H is ample, then it is automatically nef and log big. But in general, nef and big is much more general than ample line bundle. Okay, the restriction of H to the image of every stratum of XD, X delta is nef and big, is the definition of nef and log big. Then the same vanishing theorem holds for every P, every positive P and every Q. Okay, so by using this Reed-Fukuda type, we can recover Kawabata-Fiebeck vanishing theorem. Kawabata-Fiebeck means omega tensor nef and big divisor has no higher cohomology. Okay. So this is this type of vanishing theorem is necessary for generalized Kawabata-Fiebeck vanishing theorem. But I think for many applications, for example, base point free theorem, Kohn and contraction theorem, and rationality and so on, this type of vanishing theorem. So it is ample case is sufficient, I think. Yeah, and the proof of this one read Fukuda type is much more general, much more difficult than theorem 10, I think. Yeah. Okay. Okay, thank you very much.
Any question?
You said that you intended to apply this to the study of singularities worse than KLT.
Yeah.
Can you give some example of results you might try to achieve for more complicated singularities?
Yes. Sorry, I have no good example, but now I'm checking fundamental result, Kohn and contraction theorem, and base point theorem, and property of log Canonical singularity, log Canonical centers, and so on, holds for complex analytic setting, I think. And in order to apply minimal model program for the study of complex analytic singularities, I think it's very natural to consider small open neighborhood of some given point. But the formulation of BCHM does not work. It's only work for quasi-projective varieties. So we need some we need assumption everything is quasi-projective in everywhere. So I tried to generalize everything for complex analytic setting. Yeah. So sorry. Now I have no good examples of our results. Yeah. Now I'm working. Yeah.
But for KLT singularity, even it's not algebraic, the minimum program over it's already known, right, by the work of Nakayama.
Yeah. But yeah, Nakayama, yeah, main idea is Nakayama's paper in 1980s. But of course, he only treats Q divisors and KLT pairs, and yeah, the setting is slightly different from recent framework. Yeah, his formulation is not suitable for PCHM and so on. So we have to reformulate and and update their techniques for PCHM and after that.
Okay, thank you. Any other question? So if no, I mean, before we approach again, can we post your lecture recording of your lecture online?
Yes.
Okay, thank you.
Okay.
So let's thank Osamu again for the great talk.
Thank you very much.